Okay, a harder problem. When blood is donated, sodium oxalate solution is used to precipitate calcium 2 plus, which triggers clotting. A 122 milliliter sample of blood contains 9.70 times 10 to the negative fifth grams of calcium 2 plus per milliliter. A technologist treats the sample with 100 milliliters of 0.1550 molar sodium oxalate. Calculate the concentration of the calcium after the treatment. Calcium C2O4, so calcium oxalate. The Kc value for that is 2.3 times 10 to the negative ninth, and here answer in scientific notation. All right. So how we go about solving this equation with this problem is just we want to first understand what's happening. So what's happening is the blood has calcium in it, and that calcium causes clotting, which will the calcium which causes the clotting. And to prevent that from happening, the doctors put in sodium oxalate, which when dissolved in water, the oxalate combines with the calcium, which removes a lot of the calcium out of that blood, reducing the clotting. So taking a look at the equation, I always like to write the equation first. So calcium 2 plus aqueous plus C2O4 2 minus aqueous goes to C2O4 solid. C2O4 solid. All right. This is the equation of what's happening. The calcium from the blood and the oxalate from the sodium oxalate combine to form calcium oxalate. So what we want to do is first calculate the moles of the calcium 2 in the blood and the moles of oxalate in the blood after and the moles of oxalate in the sample that is injected into the blood. So to find the moles of the calcium in the blood, we are looking at a 122 milliliter sample of blood, and there are 9.70 times 10 to the negative fifth grams of calcium per milliliter, and that gives us the value of 0.011834 grams of calcium 2 plus. Okay, now we have the grams, now we want to find the molar mass. So 0.011834 grams of calcium 2 plus. The molar mass is, there's 1 mole. For 1 mole, it is 40.078 grams. Okay, so and then that gives us 0.000295 moles of calcium 2 plus. So that is how much calcium 2 plus we have. I'm going to circle that. Now, we want to find how much oxalate we have. It says we have 100 milliliters of 0.1550 moles per liter of sodium oxalate. We can change that 100 milliliters to 0.1 liters, so it works out nicely. So 0.1550 moles for every liter and of sodium oxalate, or just the oxalate. And then that gives us 0.0155 moles of the oxalate, or the C2O4 moles of C2O4 2 minus. All right. These are how many moles of each substance we have. Now, we want to find the limiting reactant to see how much of whichever ion is left over. So the limiting reactant is, since this reacts in a 1-to-1 ratio, I'm going to underline this. This reacts in a 1-to-1 ratio. We can clearly see that the limiting reactant is the calcium, because only 0.00295 moles react with 0.0155 moles of the oxalate. Now, to find how much oxalate remains, we need to do is subtract the 0.0155 moles of that, 5 moles of that, minus the 0.000295 moles of the calcium, and this will give us how much oxalate is left floating around in the blood. Well, and so, and that is 0.015205 moles of C2O42 minus. So that's how many is in the blood currently after the calcium after the calcium oxalate is formed. And we know how much calcium. Actually, this number is no longer of use. We know how much calcium oxalate is formed because all of the calcium has reacted to form that, and there was only 0.000295 moles of calcium, so therefore there are 0.000295 moles of calcium oxalate. So let me clear this up. And write down what we have so far. So we have 0.000295 moles of calcium oxalate, and we have 0.015205 moles of oxalate. 042 minus. Okay. Can erase this. Now, we're going to want to put these values into an ice table somehow. So what we need to do is we need to find the total volume of this solution, which is 122 milliliters plus 100 milliliters, which is 222 milliliters, or 0.222 liters. Now, all we need to do is just find the molarity of calcium oxalate and the oxalate by dividing the moles by the liters. So 0.000295 moles per 0.222 liters gives us 0.00133 molar calcium oxalate. So that is how much is floating around moles per liter. Now, I'm gonna parentheses this, and now we need to find this one. Same process: 0.015205 moles per 0.222 liters, which is 0.068685 molar. So of oxalate C2O42 minus. So now that we have this, gives us the values for our initial concentrations for the ice table. Now, all we need to do is shove this value. Now, let me erase this. These two values, and I have them written down here, so I can into the ice table. So this, this. Okay, so this is the ice table we have. Yeah. And then currently we have zero. Hold on, give me a second. Yeah. Okay. Currently we have zero calcium remaining because all of that calcium was just put into the calcium oxalate. So we have none of that initially. Now we have floating around. This is the excess that was unreacted oxalates. We have 0.0685 molar, and we can ignore this because it is a solid. Now, since these react in a 1-to-1 ratio, all we need to do is just add, x for the change, so plus x for each, and that gives you x and x plus 0.0685 molar. Okay, now the K's P was given, and that is equal to 2. Actually, hold on, let's write the K's P expression. So K's P equals the concentration of C2O4 2 minus times the concentration of Ca2 plus. So the K's P was given. It is 2.3 times 10 to the negative ninth, which is equal to x times x plus 0.0685. Now, all that's needed is algebra in this part. I'm not going to do that right here. It's just a lot of work and I don't have enough space. So x is equal to the concentration of the calcium, Ca2 plus, and that value is equal to, once you do the math here, 3.36 times 10 to the negative eighth moles per liter. There we go. That is the answer to the problem.